dark matter was first proposed because some of the universe's mass appeared to be missing. But why was it missing? What took it? What's wrong with the mass that we see that it is somehow deficient? Well, consider the Coma Cluster. This is a cluster of galaxies 321 million light years away in the region of the North Galactic Pole. Like everything in space, the galaxies are moving, and like almost everything in space, they're not only moving, but orbiting. What they're orbiting is the center of mass of the cluster, and using techniques we will study later, we can measure how fast the galaxies are moving in their orbits. In the 1930s, this dashing Swiss astronomer Fritz Zwicky set out to find the mass of the Coma Cluster. He did this by measuring how bright it was, and then he calculated how many stars would be needed to make a galaxy look as bright as the Coma Cluster galaxies from 321 million light years away, and added up all their masses. This gave him the mass of the cluster. Remember, the mass of the cluster is what makes the galaxies orbit around the cluster's center. For any individual orbiting galaxy, we can treat all of the mass interior to its orbit as if that mass were concentrated at a single point in the middle. The effect of the mass exterior to its orbit can be shown to cancel out. So the interior mass provides the cosmic string that prevents the galaxies from flying off at a tangent to their orbits around the center of the cluster. Zwicky measured how fast the galaxies were orbiting, and he found a little problem. For the mass he had calculated and the speeds he had measured, the cosmic string should have broken. The galaxies should be flying off at a tangent and not continuing to orbit. In other words, the galaxies are orbiting the center of the Coma Cluster too fast. In order to stay in their observed orbits, there would need to be some extra mass in the middle, providing a stronger cosmic string. This drew him to the conclusion that some of the mass of the Coma Cluster must be non-luminous. In fact, more than some of the mass must be non-luminous. A lot of the mass must be non-luminous. According to his calculations, 90% of the mass of the Coma Cluster must be dunkle Materie, or dark matter. Other astronomers were stymied, and no one shed any more light on this subject, see what I did there, until the 1970s. Vera Rubin was studying not galaxy clusters, but individual galaxies, and she reached the same conclusion as Zwicky. Those crazy galaxies were just rotating too fast. Their cosmic strings should have snapped, and the stars within them should have blown off at a tangent. It's important to look closely at this graph of what was expected in order to understand why there was a problem. On the horizontal axis, r is the orbital radius, or the distance from the center of the galaxy. And on the vertical axis, v is the orbital speed of a star at that distance. Remember, the cosmic string is stronger with more mass interior to a star's orbit, and as we proceed outward from the center of the galaxy, each star's orbit has progressively more mass inside it. Why then do we expect slower orbital speeds as we move outward? The answer lies in the effect of the orbital radius. Although the string gets stronger with more central mass, it gets weaker with a larger distance between the star and the galaxy's center. Remember the inverse square law. When gravity acts as the cosmic string, as it does in this situation, its force weakens as the inverse square of the distance. Therefore, we expect the star's orbital speeds to decrease as we move away from the center of the galaxy. But wait, why do we expect an increase right at the beginning of the graph near the galaxy's center? Near the galactic center, the stars have a greater density, so the effect of additional interior mass as we move outward from the center is intensified, and this overwhelms the effect of weakening the string by lengthening it. So as you can see, the observations deviated from what was expected by quite a bit. Although they agreed with the initial increase in orbital speed as we move out from the center, the speeds just seemed to keep going up and up without stopping instead of decreasing with radius as expected. The conclusion was that there must be some missing non-luminous mass strengthening the cosmic string as we move out from the center. This is dark matter. Let's compare the orbital speeds of stars to some orbital speeds with which we have experience, namely the orbital speeds of points on a solid body. This is called a record player, which is an ancient device that people used to use a long time ago to listen to music. The record is the solid spinning disc. If you were to glue a penny to the disc, each rotation of the disc would cause the penny to cover distance 2 pi r, where r is the penny's radius from the center. So as you increase r, the distance covered by the penny in one rotation would increase by an amount that is proportional to r. It takes the same amount of time for a penny on the outer edge to complete one rotation as it does for a penny near the center to complete one rotation, so the speed v of the penny is also proportional to r. That's what happens when the whole thing spins as a solid disk. A plot of v as a function of r would be a straight line. With bodies orbiting a central mass, something different is going on. They don't all revolve together as if they were on a solid disk. Indeed, Kepler showed us that planets closer to the sun revolve faster, while the outer planets have a much slower speed. The inverse square law tells us that the outer planets' cosmic strings are progressively weaker the farther out they are from the central mass they're orbiting. Therefore, their speeds are slower. A plot of v as a function of r would show a decaying speed. With galactic rotation, the situation doesn't seem to fit either of these categories. As we increase r, v doesn't go up and it doesn't go down. It stays constant. This tells us something, not only about the mass, but about the distribution of mass within the galaxy. Let's put this together using some equations. We'll take little m to be the mass of the orbiting star, v is its speed, and little r is its distance from the galactic center. Big M is the mass of the galaxy interior to the orbit of the star. And remember, big M will increase as we move out from the galactic center, and it encloses ever more stars within the orbit we are considering. So big M is a function of r, and that's why we're writing m with r inside parentheses. That means m as a function of r. The net force on an object of mass little m moving in a circle is little m v squared over r, where v is its speed and r is the radius of the circle in which it moves. This net force is generated by gravity. Therefore, mv squared over r can be set equal to the gravitational force, which is given by the law of universal gravitation. F gravity equals g big M little m over r squared, where big M is a function of r. The first thing to notice is that the little m's cancel, and if we rearrange things, we can write it this way. Big M as a function of r equals v squared r over big G, the universal gravitation constant. This is why, for the solar system and other situations where the interior mass is constant and Keplerian motion applies, v squared is proportional to 1 over r, or as it is written here, v is proportional to 1 over the square root of r. Note that the outer planets enclose more mass within their orbits than the inner planets do. The extra mass that they enclose does strengthen their cosmic strengths, which would tend to make them orbit faster. However, this extra mass is negligible compared to the mass of the sun at the solar system's center. So from the perspective of the cosmic string, it's as if they didn't exist, the interior planets, not the sun. The animation makes it look like the sun is small, but we need to remember that it comprises 99.8% of the mass of the solar system, and the remaining 0.2% is mostly Jupiter. So the outer planets move much more slowly than the inner planets do. And we expect to see this for galaxies as well. As we move out from the center, the speed should decrease, but it doesn't. On the galactic outskirts, the speed of individual stars does not seem to be tapering off. Past a certain point, the speed does not seem to decrease at all as we move out from the center. This is what the Andromeda Galaxy is doing. Andromeda is our sister galaxy, and it's a large, hazy patch in the sky, several times as large as the full moon. However, you won't be able to see it without super dark skies and very little light pollution. We will be colliding with Andromeda in about 4 billion years, and here's an animation of that, what that collision will look like. Getting closer and closer. When galaxies collide, most of the stuff within them doesn't actually hit. So we probably won't actually, our planet probably won't actually hit anything, but the sky will certainly look different 7 billion years from now. Since Andromeda is so close to us, where by close I mean 2.5 million light years away, we can study it more easily than we can some other galaxies like the ones Fritz Zwicky was looking at in the Coma Cluster. This is the galaxy Vera Rubin was looking at when she made her famous measurements of its rotation and generated the rotation curves that continue to perplex astronomers today. Something is making that galaxy rotate faster than it should. But what? Thanks very much to our solar siblings for these great slides.